Okay, here we go. So I made a mistake at the end of the proof of Cauchy-Inequalities, and I just want to correct it here. So you remember what we were doing was we had that sequence of nested triangles, right? And then in the limit, if you take the intersection of all those triangles, you get this point z naught, right? And then you you linearize f at z naught. So you write f as z naught plus f prime at z naught, z minus z naught, plus some error, right, where eta goes to 0 as z goes to z naught, right? And remember what we wanted to get was a bound on the integral of f over the boundary of some tiny triangle delta sub n, right, where you had fixed an epsilon, and then you'd chosen the delta sub n so that on the boundary of the triangle, epsilon was smaller than, eta was smaller than epsilon, right? That was the thing, right? So delta sub n was chosen so that eta was small. Eta was small there, right? And so then our game was use the linearization, right? So you say get that like this thing is equal to this. So this was pointed out, I forget by who, but one of you pointed this out at the end of class after most people had left. Right. So we wanted to get some bound on this, right? And the point was that because this thing this thing has an antiderivative, the integral over this closed loop was 0, right? And so we thought we're only left with this thing. We were left with this thing, right? And it's at this point we want to apply the triangle inequality for complex integrals, right? Which says that that this integral is controlled by the supremum of the absolute value of this over the supremum of the absolute value of this as z ranges over the curve times the length of the curve, right? So I wrote up something that was wrong last time, but I wrote something like this is less than I did something anyway. I wrote up something wrong. It should have been we should have used the triangle inequality at this point, right? And then the point here was that eta is smaller than epsilon. This distance was smaller than the perimeter divided by 2, and then this distance is the perimeter, right? So you get this, right? And then we showed that that times anyway, we showed that could get arbitrarily small. We could make things arbitrarily small. So anyway, so that's the right way it should have been written. Okay, and that gave us the proof of Cauchy-Inequalities that we could, that whenever you have a holomorphic function, you're integrating over this, the boundary of a triangle, you get 0. Okay, so let me erase that. Is it okay if I erase it? Seema? Is it okay if I erase it?
Oh, me?
What's your name?
Sumi?
Sumi, excuse me.
Yeah, it's fine.
Okay. Okay, so Okay, so the next thing we're going to go for is the existence of local existence of primitives. So you say, well, if you have D an open disk in C and F a function in G to C, if F is holomorphic, then F has a primitive on D. Okay. So who remembers how we do this? Anybody want to tell me how to do this? You should. I'm sure you read it. How do you do it? Yes. Jaden?
Pick a point, and so you can translate the disk to be centered at the origin.
Mm-hmm.
Given any point, draw like a line, a straight line, a horizontal line, and then a vertical line to that point. And because of this theorem, you can sort of construct a triangle, and then you get the integral like from that point to that point is just the distance between them.
Yes, yes. So, right, so the proof, basically what you do is you just, we're trying to show that it has a primitive, and what we do is we construct a primitive, right? So you say, so first off, just assume without loss of generality, assume that B is centered at the origin, right? It's some disk of some radius centered at the origin. Okay, right? And then you define a function, right? So for any z in your disk, you define capital F as the integral over some curve, what do we call it, gamma sub z of F. Okay, so you have your disk centered at the origin, right? You have some point z, and you create this path, this curve gamma z, by just going along the real axis and then going vertically. So go horizontally and then go vertically, right, to the point, and call that gamma z, right? And then you define f of z, capital F of z, as the integral of little f over that curve, right? And then you show that this thing is going to be the antiderivative. Okay, right? And the proof of it, as Jaden said, is basically just uses the Cauchy theorem, right? So you say, well, look, right? We want to show that that this guy is the antiderivative, right? That the limit as f of z plus h minus f of z over h as h goes to 0 is little f, right? That's what we want to show. And so we consider f of z plus h minus f of z, right? Well, right, if I think of I'm going to just draw this as my z plus h. Okay. So here's my z plus h. F of z plus h would mean I have to go a little bit farther out and then up like that, right? So that's my gamma of z plus h, right? And you see, so if I subtract it, right, then I'm going to get the integral of this guy over z plus h, the integral of this guy over z, right? And you subtract it off, and you see that you're going to get if this is my z, and this is my z plus h. Then what you get is a curve that goes down and then to the right and then up, right? Right. So you get this guy, right, going down, right, and then up. So it's the integral. It's the integral over that thing, down, right, up. Okay. But then you use the Cauchy theorem, and you say, well, look, I can add in a curve going this way, right? And also add in a curve going this way, right? So that's going to give me a 0, right? Because I'm going in opposite directions, right? So those guys will cancel each other out, right? I can also add in a curve going from here to here this way, and a curve going from here to here in the reverse direction. And so I haven't changed my integral at all, right? So this is the same thing as the integral over this going up, right? This going up, and then adding in going this way and that way, and also this way and that way. Right? So down, right, up like that. Right? And you break those up into so you see that you can get out of that, you can get, of course, this the rectangle going around like that, plus the triangle. I get one triangle, right? And I get this guy. We got the path going from z to z plus h. Right. Now these two things are 0 because of Cauchy Inequalities. Right. And so the integral, this difference that I'm looking at is just this thing here. Right. Okay. Right. And you say, well, okay. Now we know that since f is continuous at z, we can write f of w is f at that fixed point z plus some function, which they call phi of w, where the limit of phi of w is 0 as w goes to z. Right? By continuity, right? This is true. Right? You know that the limit of w as limit of f of w as w approaches z is f of z. That's all we're saying there. Right. So then we rewrite so we write f over that path from z to z plus h. We can write as just this constant f of z plus phi of w dw as w goes from z to z plus h. Right. Right. But this first part, of course, is constant with respect to w. So we can pull that out, right? This is integral of f of z dw over that path, and phi of w dw over that path. Right? Well, f of z was constant, right? So this is just the integral of dw, the integral of 1 from z to z plus h. But that's just h, right? Because you're going to get z plus h minus z. So that's just h. Right? So you get f of z times h for that part. Right? And then the second part, right? You know that this thing in absolute value is controlled by the supremum of the absolute value of phi, right? Which goes to 0. Times the length of this times the absolute value of h, right? So this is controlled by the supremum of phi of w, right, on the curve where w ranges on the curve from z to z plus h, right? Times the length of h, right? Right. But so when we come back and look at this thing, right? This thing is this whole thing divided by h, right, as h goes to 0, right? Well, as h, when you divide this by h, right, so what we get is that the limit of f of z plus h minus f of z over h as h goes to 0, we get f of z plus this thing that goes to 0. Right, as h goes to 0, right, the supremum, phi goes to 0, because phi lives on, phi goes to 0 as w goes to z. Right. So that's it. Okay. So what does that give you? That gives you that we can create antiderivatives. Yes, Nico.
How do we know it's controlled by the supremum?
This is the triangle inequality again. So, right, we had that, whenever you've got a function, you're integrating a function over a curve, then the absolute value of it is controlled by the supremum of the thing as the variable ranges along the curve times the length of the curve. Right, times the length of the curve. Here the length of the curve is absolute value of h. Right, and this is the supremum. Okay. So, and that just comes from the definition of the integral of a function over a path, plus the standard triangle inequality. Everybody okay? Yes, Aaron.
If we have a less than or equal to sign for that triangle inequality thing, why does it become an equal sign in our proof?
So this thing is less than or equal to this, right?
Yeah.
Now the limit when we take the limit as h goes to 0, this thing becomes 0.
It just becomes.
Yeah,
Okay.
this is 0. So yeah.
So it doesn't really matter.
Yeah. Yeah. So maybe it makes sense to think of this thing separately, right? This is a term as h goes to 0. This term goes to 0, right?
Yeah.
So yeah. Okay. Everybody all right? Okay. So what does this give us? Right? It gives us the existence of antiderivatives in the disk, and so what that gives us is something nice. What's generally called Cauchy's theorem. Right? That if f is holomorphic in disk, then and gamma is any closed curve in that disk. So it's an open disk. Then the integral of your holomorphic function over the closed curve is 0. Okay, right. So we don't have to worry about triangles or simple things anymore. Right? You can have whatever closed curve you have, right? As long as it's a closed curve, then the integral over it will be 0. Okay, and Stein gives kind of a simple extension. He says, well, you could also have something like this. You could have an open set, and this open set may have holes in it. Right? Doesn't matter. You have some open set. He says, as long as you have if you have a disk, and as long as the disk's interior is contained in the open set, then the integral over the boundary is going to be 0. Okay, it's not really that big. It's not really that serious an extension. Yeah. So yeah. Anyway, we'll just leave it. Okay. 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 So I think I'm gonna I'm going to skip a couple of the calculations that Stein goes over. But if I have time at the end, I'll get back to them. So let me just go on with the theory for now, and then I'll come back to the applications if there's time at the end. So Stein shows that you can use Cauchy's formula to show that the Fourier transform of the Gaussian is still the Gaussian. This is something that we're going to use later. I presume he does it because we'll use it when we get to the Fourier transform later, chapter 4. But I think it's more. Let's get to the important stuff first, and then we'll get to the kind of the dull calculations later. It's not that exciting. Okay. So Cauchy integral formula. Okay, so here we go. We have a function, it's holomorphic on some open set. Okay, and then and then you have a disk, D, a disk whose closure is contained inside of omega, and we let C denote the boundary of D oriented positively. Okay, so counterclockwise. Then for any point Z inside the disk, that point, the value of f at that point can be calculated as the integral over the boundary of f of zeta over zeta minus z divided by 2 pi I. Okay. So this is saying that all the values inside the disk are determined by the values of f on the boundary of the disk. Okay, so like all the information, it looks like there's a lot of information there, but it's actually determined by f on a one-dimensional thing, which is pretty interesting. Okay, so the proof goes like this. You say, okay, you have your disk D, and you have some point Z inside of it. And what you do, actually, let me write it. What you do is you create a curve called gamma delta epsilon. Okay. And so that is, you take a little disk here of radius epsilon around Z. Okay, so radius epsilon, and then you take a kind of a path of width delta. Okay. And this total path here, going counterclockwise around, and then diving in, and then going going clockwise around the little circle, and then coming back, and then going around like this. This is the path gamma. Okay, and right, and so the point is that so observe. Notice that the integral f is holomorphic. I'm sorry, that f of zeta over zeta minus z d zeta if we integrate this thing over gamma, we get 0. Right? Because this is holomorphic there, and this is also holomorphic there, because we stay away from z. Right? The only place where this fails to be holomorphic is at z, when zeta equals z. Okay, so that's going to be 0 by Cauchy's theorem. Okay, and then okay, so that's our first observation, and then the second observation is that in the limit, so if we take the limit as delta goes to 0, right? Then these two paths are going to become arbitrarily close to each other, and so the integral is just going to cancel itself out. Okay, right? We'll have one path going this way. We'll have the other path going this way. So those integrals will cancel, right? And so so when we take the limit of this thing, right? That's 0, but it's also the integral over the outside guy, right? So the integral over what am I calling it? C, of course. The integral over C plus the integral over the inside guy, which we'll call gamma sub epsilon. Okay. So right. So this guy on the outside is C, right? Right. The guy on the outside is C. The guy on the inside, going in the opposite direction, we'll call gamma sub epsilon. Okay. Okay. So we're going to think about, right? We want to right. We want to say something about, what am I saying here? Right. We want to say something about this, right? That this is going to be f of z. So we're hoping that this is going to be negative f of z, right? That's our goal. Okay. I want to show this is negative f of z. Okay. Okay. Actually, let me call it c sub epsilon, because that's how I've got it in my notes, and probably how Stein has it in the book. Okay, so I think I'm going to go over here. Okay, so we play a trick. So we say, well, let's look at this thing. F of zeta minus z d zeta. Right? And we're going to rewrite it as f of zeta minus f of z over zeta minus z. Plus f of z over zeta minus z d zeta. Okay. Right. So we do something simple, right? We throw in a 0, right? We subtract off f of z, we add on f of z. Okay. And the reason we do that, of course, is because this thing is the difference quotient, right? And we're going to take advantage of the holomorphicity of f. Right? So this we have control over this thing, right? So often in analysis, what you do is you throw in things that you have control over to sort of mod out some difficulty of the problem. Okay, So yeah, right. So we have this guy. We have this guy, and we have this guy. Okay. Now, what's the point here? What can we do with this guy? Well, yeah. Go ahead, Noah.
Like as epsilon approaches 0,
Yeah.
that's gonna approach like f prime of the
Exactly. Right. So this thing. The point is that this thing is bounded. Right. It's bounded. Right. And so when we do the triangle inequality on it, if we're looking at the size of this term, well, by the triangle inequality, it's going to be controlled by the bound times the length of the curve, but the length of the curve goes to 0. Right. And so this guy vanishes. Right. So so if we think, let me call this guy term 1. This guy term 2. Right, so term 1 goes to 0 as epsilon goes to 0. Right, is that clear, everybody? Right, now this thing, right, the absolute value of term 1 is controlled by right, the supremum by some bound times the length of the curve. Oops, times the length of the curve, right? But as epsilon goes to 0, the length of the curve goes to 0. So we get that bound times 0, right? So this is 0. Okay, so that first term goes to 0, right? And then this sort of thing here is just a sort of standard integral, right? You say, well, here we're going counterclockwise, right? So we think of this as the integral, right, let z be, what should I call it? Of course it's zeta. I'm going to let zeta be, zeta of t be z plus epsilon e to the I t as t ranges from 0 to 2 pi. And so, right, this by definition, this is the integral from 0 to 2 pi of epsilon I e to the it over this minus z, which is just epsilon e to the it. dt, right? And so I get 2 pi I. Right? So C.
If you're going clockwise, do you have to add a minus sign?
Thank you. That's exactly why I was pausing. Yeah. So yeah, I'm actually going that way. Okay, you know what I mean. Okay, so yeah, so what do we get here? We get we get that that this term, right? So 1 over 2 pi I as c goes to 0, this turns into negative f of z. Okay, which is what we wanted, right? Right. Yeah, which is what we wanted. Okay, so that's the end. Is that okay? You guys look kind of confused. Why is there a cloud of confusion? Are you tired? Yes.
What does the so we have the magnitude part 1 is less than or equal to n times L of
The length of the curve.
length of
Uh-huh.
C epsilon,
Mhm.
and what does that downward zero mean?
Oh, so it means it decreases to 0.
Oh,
right?
okay.
As epsilon goes to 0, this is going right as epsilon goes to 0.
Thank you.
Yes.
So m is just some value that's greater than supremum of f epsilon or f zeta minus c zeta.
Exactly. Right. The point being that this is going to converge to f prime of z, and so we know that as this gets arbitrarily as this goes to 0, this is a bounded term. So. Okay. So yeah. Right. Okay. Okay, so that gives us Cauchy's integral formula. So the thing we're going to do next is the derivative form of Cauchy's integral formula. So for derivatives. Okay, so here's how it goes. So there's sort of two parts to it. One, so let's say that f, so we have omega an open set in C, and we have f, a holomorphic function on omega. And so it's got two parts. First, that one, f is infinitely differentiable. Or if you like, indefinitely differentiable. That's, second, again, if D is an open disk in omega, whose closure is still contained in omega, and again, we let C be the boundary oriented positively. Then, for all points in omega, all points in D, we have a formula. We have an integral formula for the nth derivative. So it's n factorial over 2 by I, the integral of f zeta over zeta minus z naught to the n plus 1 d zeta. So we have an integral formula for the nth derivative for all derivatives. Okay, so the proof, I'm just going to show how you get from the first derivative to the second derivative. that's enough, right? Once you have that, you can just repeat that. So you say, well, look, by the Cauchy integral formula that we just proved, that tells us that we can write f as that we can write, then we can write f as an integral, of course. Right? And what do we want to show? We want to show that the limit of f of z minus f of z naught over z minus z naught minus the expression, right? 1 over 2 pi I f of zeta over zeta minus z naught squared d zeta is 0, right? As z goes to z naught. Right? Right. This is supposedly, this is the term that's supposedly our derivative, right? We want to show that the derivative actually, the difference between the derivative and this term is 0, right? Okay. So okay, so we just sort of plug in by definition, right? So by the theorem, we get f of z minus f of z naught over z minus z naught. We just use our formula up here, right? So we get 1 over 2 pi I this zeta minus z d zeta minus 1 over 2 pi I f of zeta minus z naught d zeta. Everything divided by z naught. So that's just the definition. I mean, that's just using Cauchy integral formula, right? And so we can rewrite that as 1 over 2 pi I integral f of zeta over z minus z naught 1 over zeta minus z minus 1 over zeta minus z naught d zeta. So you just combine the integrals, move some constants in. Okay. That is using childhood algebra. Right, we're going to get zeta minus z naught minus zeta minus z. That gives us a z minus z naught on the top. That will cancel with the z minus z naught on the bottom, right? And so we get this over the common denominator. Okay. Right. So that's this first term here. Right. That's this first term here. Right. So just plugging that in, right? This is going to be the limit as z goes to z naught of 1 over 2 pi I f of zeta 1 over zeta minus z, zeta minus z naught, minus 1 over zeta minus z naught squared d zeta. Right? It's just out. You know, we're not doing anything. It's just, you know. Okay. And so again, doing nothing, we get the limit as z goes to z naught of z minus z naught over 2 pi I times f zeta over the common denominator again. So, okay. Okay, so you know, don't you know, yeah, we haven't done anything at all. All we've done is just like, you know, childhood fractions. Okay. Nobody's smiling. Why are you not smiling? It is. Are you okay? Everybody all right? Yes. I guess not. Should I just, in the future, should I just skip all that and just write the end? Okay. Okay. Okay, so now we have to use kind of a geometric observation. You say, well, look, our point z naught, let's let d denote the distance to the boundary. Okay, the distance, and remember z is going to z naught. So let's assume that z has entered this disk. Okay, so let d denote the distance of z to the boundary, and assume that the distance of assume the distance of z to z naught is smaller than a half of that. Okay. Okay. So then, for zeta on the boundary, we know that the distance of zeta to z naught is bigger than or equal to d, and the distance of zeta to z is going to be smaller than, bigger than d over 2. Okay, so now I'm going to come back here. Okay, so now if we take the absolute value of this, if we look at the size of this thing, well, right, one, we know that you know, f is a continuous function. F is holomorphic. It's continuous on this curve, right? And so there's a bound for it, right, by the extreme value thing. Right? This is a compact set. You've got continuous function on a compact set. Okay. So you know that the supremum of the absolute value of this is bounded by some m, right? So we get, this is smaller than z minus z naught over 2 pi times m times the length of the curve times the length of c, right, over, right, well, you know, each of these things is greater than d in absolute value. So, you know, the reciprocals are smaller than 1 over d, right? And that 2 will get rid of this 2. Everybody okay with that? Right? right? We're just using the triangle inequality again, right? So we take the the supremum of the absolute value of the integrand, right? This thing is controlled by some constant, right? This thing is controlled by some constant, and then these guys are all controlled by 1 over the lower bound, right? Right. Okay. And so we get this, right? And then as z goes to z naught, we get 0. And so what was the point? That the derivative is this thing. We show that the distance between the difference quotient and the supposed supposed formula is 0, goes to 0. Yes.
Later on, they show that you can do this like in a way that seems much simpler, just by showing it's analytic first.
By showing it's what?
By showing that it's analytic first.
Yes. 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 Yeah.
Well, why don't we just do that? Like, is there something in this proof in particular that is?
I'm sorry, I don't know the answer. Let me think about the answer to that. Yeah.
In terms of the logic, it might be required for the purpose of showing that the power series exists for the
No,
analytic.
no. Like they specifically note that you could use that as a proof of this smoothness.
Oh, okay. I missed that.
Let me think about it. Let me take a look at it because yeah, I will give you that answer. Okay. 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 So from here, it's sort of typical to give a bunch of nice results that follow from these formulas. The first is so-called Cauchy Inequalities. And it's just an immediate consequence of the Cauchy Integral Formula for derivatives. So again, right, you've got f on some open set, and it's holomorphic. And you've got and you've got some disk centered at some point z0 and of radius r, where the closure of the disk is contained in omega, and c is the boundary again. Then the nth derivative is controlled by n factorial times the supremum of f over the boundary over r to the n. Okay, and this is just an immediate consequence of the formula. Right? You say, well, look, by the formula, this equals, right, n factorial over this over the boundary, this minus z naught to the n plus 1 d zeta, right? Right, and right, and then you just use the triangle inequality, right? This is controlled by n factorial times times the supremum of the absolute value here, right? Well, that's just f of c over r to the n plus 1, right? Times the length of the curve, which is just 2 pi r, of course. Right, we have the 2 pi here. Right, so we lose the 2 pi r, we get the, and that's it. So it's trivial. Okay, so that's so-called Cauchy inequalities, which doesn't seem that great, but it's what gives you Liouville's theorem. So this is the theorem. How do you pronounce this word?
Liouville?
Liouville? How do people pronounce this word?
Liouville?
I say Liouville.
Liouville. Yeah. So I mean, this is of course a French word, but in America we all say like Louisville, basically. We say it incorrectly, but anyway, I'm going to call it Liouville's theorem. Okay, so the theorem, of course, says that if f is entire and bounded, then it must be constant. Right. So what's point? Point is that if you fix any z, then by Cauchy's inequalities, you know that this is bounded by right. If you have a bound over the entire plane, right? Then right. So right? The bound depends on the curve. The bound depends on the curve, but if the bound doesn't depend on the curve, then you're gonna get a bound like this for every r, right? So normally, right, if you didn't have this, well, you'd have a bound, but the bound would depend on the value of the function on the curve. But since the value doesn't depend on the curve, you have this uniform bound over for all r, right? So for all r, right, which tells you that the derivative is constant. Yeah, go ahead.
Don't we want the derivative 0 here, not derivative constant?
I'm sorry, the derivative is 0, sorry. The derivative is 0, and so the function is constant. Thank you. Thanks. Yeah, I'm getting old. Yeah, I have to say that my children are always reminding me, they're like, Dad, you have no memory anymore. Dad, Dad, we just told you that yesterday. And I sometimes I suspect that they're gaslighting me. Right? They're like, Dad, you said this yesterday. Like, did I? Yeah, it's kind of scary. But, yeah, thank you. Yeah, to correct me, keep on correcting me, because I'm afraid there was this one professor who I will not give the name of at the University of Chicago when I was a graduate student, and he would say, like, suppose you've got a manifold M, right, and then and blah 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 blah, and the joke was that he used only two symbols, one of which was a gamma rotated 45 degrees clockwise and an alpha rotated 45 degrees counterclockwise. Right. So he was like regarded as like a really terrible teacher. But now that I'm in my 50s, I'm like, I can't make fun of anybody anymore. Okay. yeah, just correct me. If it's wrong, just correct me. Okay. Okay, so the last thing we're going to get, I think maybe we'll do the calculations next time, is another corollary of Liouville's theorem, the fundamental theorem of calculus, fundamental theorem of algebra. Sorry. Okay, so that you have some polynomial. And if p is not constant, then you must have a root. Okay, and so the proof is by contradiction, right? Suppose that it has no roots. Suppose p has no roots, right? And what we're going to see then is that, well, in that case, 1 over p is holomorphic, right? So 1 over p is holomorphic. Okay. And what we'll see is that 1 over p is going to be bounded, and so it will be constant, which would force p to be constant, contradiction. Okay, so that's the pattern. We'll show that 1 over p is bounded, which by Liouville's theorem implies that 1 over p is constant. Contradiction. Okay, so okay, so here's how we do it. We say, well, look, say p is of the form, an z to the n plus an minus 1 z to the n minus 1 plus a1 z to the 1 plus a naught. Yeah, so if you ever need to get a homework in late, you should just come up to me and say, you said I could hand this in late. And I'll be like, okay. Yeah, I'm afraid that that is actually true. that will almost definitely work. Okay. Okay, so yeah, so I have to think of some way around it. Homework, any such requests must be emailed to me. Okay, so you get this plus a minus 1 over z plus a naught over z. Yeah. Right, and the point is, of course, that right, the point is that as z goes to infinity, then p over z to the n goes to a sub n. Right, so you can make p over z arbitrarily close to a sub n z to the n. As z goes to infinity, right? In particular, there exists a disk outside of which, right? If you're outside of this disk, then p sub z is bigger than this. Right? Because you can make these things arbitrarily close. So what does that tell you? The point is that P is bounded from below on that disk. Right? So what do you have, right? So P is bounded from below on that disk. In other words, 1 over P is bounded from above. Right? 1 over P is bounded above, outside of that disk. Okay, but you also know that 1 over P is a non-zero function. So let me continue over here. 1 over P is a continuous function on a continuous non-zero function on the disk, inside the closed disk, right? And so that tells you that, P is a continuous non-zero function on the closed disk, right? Which tells you that its absolute value has a definite distance from zero. It has a minimum value, right? Again, by the extreme value theorem, right? It's got a minimum. It's got a right. It's got a minimum. It attains a minimum value on that closed disk, right? So there's this positive disk. It never gets arbitrarily close to zero, right? What does that tell you? That tells you that 1 over P is bounded above by a constant, right? On the disk. So you have those two parts, right? 1 over P is bounded outside the disk, and 1 over P is bounded inside the disk. So it's bounded, and so it's constant. Right? So it's constant. P must be constant, contradiction. Okay, so this is like a nice proof of the fundamental theorem of algebra. Okay, that's all for today. Yes?
Is
Kai?
this the standard proof of the fundamental theorem of algebra?
It is for analysts, I guess. Yeah.
Gotcha.
Yeah. I think there are multiple proofs. Like I think Gauss proved it like 5 different ways, in his doctoral thesis or something like that. Yeah, that's something like that.
There's a proof you can get with sort of more elementary techniques, apparently.
Yeah.
If you don't need so much analysis, but this is much easier to do.
I'm not. Yeah, that doesn't surprise me. Yeah. Okay, that's it for today. See you guys later.
Can we clarify the previous question?
Yeah. So I'm sorry. I should have opened up. Are you able to write on in the discussion on Canvas? Does that work? And are you able to put mathematical notation in there?
Yeah.
Yeah. Okay. Then I'll just every time I'll open up like a discussion, and please put your questions and answers and respond to other people's questions there. Okay. Yeah. Sorry, I didn't do it this time. That's my fault.
Do before class.
Yes, please. Yeah.